All right, well, again, as I usually do at the beginning of the hour, I put up some stuff from the last hour that I just want to either refer to or comment on. So here I just rewrote Taylor's theorem again, because we're still going to refer to it. And at the end of the hour, we looked at a problem where we used the two-dimensional version, where we had a CSTR mixer with no reaction. So we had fluid coming in and theta in, and of course some volumetric flow rate. It was being mixed and it came out and theta out. And it was being cooled by a cooling coil, where the cooling coil had a VC in, a volumetric flow rate of the cooling fluid coming in, and a temperature of the cooling fluid coming in. Those are all things we can choose. We can't choose the outlet temperature of the cooling fluid. That is what it is. And we can't choose theta. Those are both determined by the system. So what we did is we wrote out a heat balance on the reactor, and we saw the heat balance on the reactor had an unknown of the amount of heat that was being transferred between the coolant fluid and the action fluid. So we had a Q that was unknown. So then we wrote, to write out an equation for Q, we wrote out a heat balance for the cooling coil, the fluid in the cooling coil. And we assumed it was pseudo-steady. And that way we got an equation for Q, but that equation for Q introduced a new unknown, theta out, theta C out. So we had another unknown. Now we have three unknowns. We had theta, Q, and theta C out. So we needed another equation. And that other equation was an equation for Q, which we did by integrating the heat transfer from the coil to the fluid, or from the fluid to the coil at each point in the coil. We integrated over the coil, and instead of integrating, we said the integral was an average, so we just took a silly average. And then we put those three equations together, and we found, well, two of the equations, we found that Q was a function of VC and theta, and it was nonlinear, because it had all these VCs in it, powers. So we noted we had to use Taylor's theorem, here it is, to write Q as a function of these two variables as Q of the value of the reference point at the initial condition, which was steady state, t less than 0, plus the derivative with respect to the first variable, dq dvc, at the steady state, times vc prime, plus the derivative with respect to the second variable, dq d theta, also evaluated at t less than 0, evaluated at the reference point, times theta prime. And we have that expression for Q, which I'm not going to rewrite here, but in particular, dq d theta we found was negative this quantity. And the rest of it, the actual expression for Q and the value of the QdVC, you have in your notes. But here we had the Qd theta, which is equal to negative this quantity. The important thing is that Qd theta was a negative number. So then when we plugged into the balance, the heat balance for the reactor, we had this equation here, the time derivative plus theta in prime, that was equal to, sorry, not plus, was equal to theta in prime minus theta prime over tau. And then this whole thing was the Q. We divided by rho VCV. And the Q was equal to the Q at the reference state plus these two terms. But when we subtracted the heat balance at the reference state, this term canceled out. And we got primes here instead of just regular variables. And we were left with this term and this term, which is this term and this term. And then we noted, let's bring all the theta primes to the other side of the equation. So here's the theta prime dt plus theta prime over tau, that's this term. And then we had minus the qd theta prime, minus, this is dq d theta t less than 0 times theta prime, over rho vcv. So that took care of this term and this term. And what's left on the other side was theta in prime over tau, and q dvc times vc prime. So, and of course divided by rho vc. rho VC. So this is the equation we had, and we noted that this is exactly in the form we're used to. A time derivative plus the first derivative times something is equal to something. And in particular, the somethings are all constants, because this is evaluated somewhere, this is a number, this is a number. This is a step change. We're given a theta in prime as a step change, so it's just a constant over t. And this is evaluated somewhere, and these are constants. So we're of the form dy dt plus a y is equal to b, where a and b are constants. And for this problem, we were given that Vc as a function of time went through a step change at t is equal to 0, but theta in did not change. So theta in prime was equal to 0. That's just the given the problem. But we already set up the problem that even if it weren't 0, we would know what to do with it. But in this particular problem, we set this term equal to 0 as the given. The point I tried to make wanted to make at the end of the hour was this whole thing here is 1 over the time constant. Because our typical form is, if you notice, this has units of temperature divided by time. So every term in the equation has to have units of temperature over time. So this has units of temperature, so this whole thing has units of 1 over time, and that's the time constant of the system. And I want you to notice that when I see a minus sign here, I get scared. Because if this whole thing ever turned out to be 0, then 1 over t would be 0, and the time constant would be infinity. We don't want infinities here. But so that was, at the end of the hour, I said there's got to be a sign error here, because I can't have an infinity. And 30 seconds after the class ended, I went back and I noticed that the theta, the QB theta, t less than 0 was equal to this. So this quantity was already a negative number. So minus this is a positive number. So there's no problem. So this whole thing is a positive number, and it's a 1 over the time constant. And we can notice that if I take 1 over tau plus something is 1 over t, that means that t is smaller than tau. Because if I invert it, t is 1 over this. In other words, t is smaller than tau from this form of the equation. You can see that immediately because I have 1 over tau plus something, let's say plus, I don't know, alpha is equal to 1 over tau, 1 over t. So if I take the inverse of this, I have t is equal, well, this is equal to 1 plus alpha tau over tau. So that tells me that t, when I take the inverse, is equal to tau over 1 plus alpha tau. Just a little bit of algebra. So you can see that t is smaller than tau because it's tau divided by a positive number. So therefore, so in particular, I have t is less than tau, where I just call this whole thing alpha. What does that mean? That means t is the time constant over which the solution changes. So for example, when we apply this to this case, and we calculate theta prime versus t, versus time, for t less than 0, it was here, and then we get an exponential, 1 minus an exponential, because we know from the solution here that theta prime of t is equal to b over a, so it's equal to d theta dvc, t less than 0, 1 over rho vcv times vc prime divided by a is times t, divided by 1 over t, times 1 minus e to the minus t over t. So this is whenever we have an equation of this form, we know that y of t, when a and b are constants, is equal to y of 0, but theta prime of 0 is always 0, times e to the minus at, plus b over a, this is b, and this is a, 1 over t, b over a, times 1 minus e to the minus little t over b. We've had this about 10 times already in this class. So what you can see is, t, big T, is the time constant over which this changes. And since t is less than tau, it changes faster than if the time constant were tau, then it would take much longer to get there. But it changes faster. Why does it change faster? Because the other part that enters into the time constant, has to do with the heat transfer. The heat transfer due to the cooling coil makes the temperature theta respond more quickly. It responds more quickly than if I didn't have a cooling coil, and it just had to cool by virtue of, for example, if theta in changed, then the temperature in the outlet would, and if I didn't have cooling, the temperature in the outlet would change only by virtue of the fluid coming in replacing the fluid going out. But since I have cooling, it also changes not just by the fluid coming in replacing the fluid going out, but also by virtue of the fact that I'm doing active cooling. So that shortens the time of response and makes the system respond quicker. And that's the physical meaning of T being less than 10. Is that good? Now we could also look to see what is the Kp. So Kp, remember, is the steady state gain, and that's equal to delta theta as t goes to infinity, divided by delta Vc as t goes to infinity. That is, it's the steady state gain, it's the change in the output is theta, divided by the change in the input. In this case, there's only one input that changes as t goes to infinity, that is in steady state. So that's equal to theta prime over Vc prime when t goes to infinity. When little t goes to infinity, then this term drops out, and I just get the coefficient here, and that's equal to d theta dVc for t less than 0 times 1 over rho Vcb times big T, where big T is this thing. So you can calculate that just from here, and here we have a steady state gain. The only other thing I want to mention here on this problem, before again asking if there are any questions, is on each of the problems we've done so far where we did a linearization, I wanted to ask, can we tell if the linearization overestimates the change or underestimates the change? So let's look at it for a second. We notice that we linearized this particular, a quantity that looked like this. Q had a complicated VC dependence. And the VC dependence looked like this. It had a VC to the B plus 1 here, a VC and a VC to the B here. Where VC was the volumetric flow rate of coolant. And we were told that B is less than 1. So if we divide top and bottom by VC, this becomes VC to the B, this becomes a 1, and this, and this becomes, I don't remember if this is actually, if there was a B plus 1 here or not. You have to check your notes if this was a B here or B plus 1. In any case, when I divide, I get something that's VC to the B in the numerator and a 1 in the denominator. So this goes to VC to a power where B is less than 1. So what does that mean? If I plot VC to the B divided by something, 1 plus something, where B is less than 1 versus VC, that's going to be some sort of concave function because B is less than 1. Think of a square root. So it's going to be concave. If it's concave, then when I do the linearization is going to be higher than the function. And remember that the higher VC, the more heat transfer I have. So what this tells me is that my linearization overestimates VC, and therefore it overestimates the heat transfer. because if you remember, UA was given as A, B, C to the B. So if I overestimate VC, I overestimate the heat transfer. So that means if I overestimate the heat transfer, then I overestimate the cooling. So that says if this is linearization, then the true one is going to be up here if VC went up. If VC went down, this is if VC went up. If VC went down, so if instead of going like this, it went like this, went down, then so if VC went down, then I have one curve that looks like this, and the actual true value would be a little higher, because I've overestimated the cooling. Any questions on that, on this whole problem? I had just run out of time, and I had 2 more minutes last time I could have done all this. But that's what happens. Sometimes the clock works against you. Questions? Again, the idea of being in class is to try to follow what's going on in class. You'll have a picture of this. You can always look at it later. Don't worry so much about writing. Try to follow what's going on in class, and if there's anything you don't follow, interrupt me. It's okay. You're allowed, not only you're allowed to interrupt me, you're encouraged to interrupt me. Some people don't like being interrupted. I like being interrupted because it's a sign that you're listening. Okay, so this was a little bit of a recap. You know, like when you watch one of these series on television, before they go into today's episode, they review a little bit of last week's episode. So this was from last night's episode. Now we're going on to new stuff. And a little bit more of a recap. Remember, we looked at problems last week where the equations themselves were linear. And then we showed how when we had linear first-order differential equations, we could integrate them. We started from this form, and we looked at cases where A and B were constant, and cases where A and B were not constant. So we did some examples there. Then we said, you know, linear is really nice, but most problems are not linear. We wish they were, but they're not. So then we said, when they're not linear, what do? Well, as long as the changes aren't too big, we could try to use linearization. When we tried to use linearization, we had to rely on Taylor's theorem. And we said, this is true in any dimension. In one dimension, it just looks like this. In 2 dimensions, it looks like this. I did an example of a chemical reactor where the rate of reaction was quadratic. So I had only one variable, that was this one. Is that my phone? I thought I shut it off. We did an example where the rate of reaction was quadratic, so there was one variable, Ca, and we used this equation. Then we did an example where we had a tank where the level could go up and down, so we again only had one variable, the level. So we again used this case. And then I wanted to give you an example where we had a quadratic one, so I jumped to this case. And this case was a little complicated because there was a lot of algebra. So what I like to do is just do one more case like this, where the algebra is less onerous, so you maybe don't get lost in the algebra. So let's look at a simple case of a CSTR. CSTR. A goes to B, V in, V, Ca in, Ca, Ca. It's just a first order reaction. But we're given that the V as a function of t goes up at a certain time. So let's write out the equation. So in this case, the algebra won't be that bad as the last one. So I've got dCA dV is equal to Ca in minus Ca over tau And let me be explicit with tau. Tau is little v, big V over little v. So let's put the little v over here and the big V over here. Minus Kc. So this is the exact equation. And remember what we do with minimization. We start out with the exact equation. Now, in this, let's think what's going to change. When V changes, what's going to change as a consequence of V changing? So I need your help here. You're listening along. I change V. What's going to change when I change the volumetric flow rate? What's that going to affect? The concentration. If I increase or decrease the flow rate, then the concentration coming out is going to change. Well, notice the flow rate multiplies the concentration. The fact that these two multiply each other and they're both changing means this product is nonlinear. So I need to linearize that product. So let's write out all the other terms. So here's the linearization. dCA dt. That term's okay, that one's fine, is equal to Ca in over tau. That's okay, because actually, let's just leave the Ca in V. And here I have middle V. But this term, and then I'm also going to have a minus Kca. That's okay also. But little v times Ca I need to linearize. So little v times Ca, that's nonlinear. That's a function of v and Ca. So this is equal to Vca at t less than 0. So the function is Vca. It's Vca at t less than 0 plus dVca dV. What is ddV of Vca? If I take ddV of this, what do I get? Somebody, this is high school calculus. What is ddV of Vca? Ca. So this is equal to Ca at t less than 0 times V prime plus V prime is x minus x0 plus dVca. I shut it off. Why does this keep on ringing? Plus dVca dCa. What is dVca of Vca? V. So plus V at t less than 0 on Ca prime. So let me make this a little move this to the left a little bit. Okay, so now I've got as Vca. Actually, let me bring the V on the outside, so I don't have to rewrite the V. Times Ca in, Vca in. And now I've got minus Vca t less than 0 minus Ca t less than 0 V prime minus V t less than 0 Ca prime minus Kca. Is that clear? So for Vca, I took the linearization and I got these three terms. So you get the algebra is much simpler because the derivative is easy to take. Now, let's do the exact for t less than 0. That was dCa t less than 0 dt is equal to 1 over v times Vca in t less than 0 minus V, this is, I want exact at t less than 0, minus Vca t less than 0, minus Kca t less than 0. So all I did is I rewrote this equation where all the variables were at t less than 0. The only variables that change are v and ca. So ca in didn't change, only v changed. So v changed and ca changed, so that's why I had to say that they're less than 0. Now I subtract, and when I subtract, I have d dt of ca minus d dt of ca at t less than 0. That's dca prime dt. And that's equal to 1 over v times. Well, notice here I have ca in times v prime. And this term and this term cancel. So now I also have minus ca t less than 0 v prime minus v at t less than 0 ca prime minus, so these terms just got inherited. This term and this term cancel. And now I have a minus k ca minus ca t less than 0 ca prime. And now what I can do is bring all the CA's to one side of the equation. dCA prime dt plus CA prime times CA prime times, well, I've got this term, so I've got, I'm sorry, this term, which is CA, I want CA primes. CA primes are here and here. So here I've got V at t less than 0 over big V. That's this term. And then I have plus k. That's this term. I took care of these terms. And what's left on the other side of the equation is CA in divided by V minus CA, actually we have both, minus CA at t less than 0 times V prime. And notice, so all I did is I rearrange this. Notice this thing is nothing more than 1 over tau at t less than 0. So I have the usual thing, dCA prime dt plus CA prime over t, where 1 over t is equal to 1 over tau at t less than 0 plus k, which is 1 plus k tau t less than 0 over tau at t less than 0. The usual 1 over k tau over tau. And that's equal to CA in minus CA at t less than 0 over V times V prime. And again, I have something of this form where A and B are constants. This is A is 1 over t, and B is this thing. This hasn't changed, and this is evaluated at t less than 0. So again, I have CA versus t, 0. So if V went up, then this thing goes up. Because I know the solution, CA, this is CA prime of t is equal to B over A, CA in minus CA t less than 0 over V, divided by A, divided by 1 over t, times 1 minus e minus t over V. That's how I get this curve here, and the time constant is big T, as usual. But here you have an illustration of how I have a nonlinear term that I linearized where the algebra is really easy to linearize. I did the same type of maneuvers here, but the algebra was more complicated. So I really should have done this problem first. First do the case with the easy algebra, where you can see what's going on, and then do the case with the more complicated algebra. Are there any questions on this, on the case with the easy algebra?
So, I understand conceptually how that original equation is nonlinear.
You understand conceptually what?
I understand conceptually how and why that original exact equation is nonlinear.
Good.
But I guess I have a question mark in terms of, like, should we be able to visualize what that looks like? Because I really have thought.
Wait. Visualize, I mean, we visualize it after we solve the equation. before we solve it. Now, sometimes you might have the intuition to be able to visualize it beforehand. In fact, we're trying to build up to that, but I don't expect you to have that intuition yet. But let me know your question, sorry.
That was kind of, because like I wouldn't, from when we were describing the math equation, I think in my head, I wasn't thinking it was going to look like that. I was thinking more like, oh, it's probably more of a square, it's like double multiplying.
Well, remember, it's not quadratic. Quadratic would be if it had a v squared. It's v times ca, where ca is a downstream effect of v. So it's not obvious a priori what the solution should be. In other words, until you've done it, you don't know. If it were ca squared, if you remember in the case of ca squared, then I was approximating quadratic. But here I'm not approximating quadratic, I'm approximating the product of two different variables. So it's not obvious until you work it out.
So all you have to be able to recognize is that the simplicity of the trend. Like there's the flow going up and the concentration going up and as long as you can recognize that there's like
Yeah, but you don't have to guess what it looks like. You work out the algebra and you see what it looks like. That is, it's nice if you have the intuition, but the way you get the intuition is by solving problems. So I understand that from the case where we did ca squared, you might have guessed that the shape may have looked a little different, but it was a different problem. So it was worth working this one out and not relying on our intuition from the previous problem.
things.
Sure. Yep.
What happened with the little v prime? We could be already.
Isn't it still here? Here's v prime. Oh, did I lose v prime? I lost v prime. Thank you. I lost v prime. And obviously, if I want kp, that would be ca prime as t goes to infinity over v prime as t goes to infinity. So it would just be ca in minus ca at t less than 0 over v times big T. So this would be the steady state. Any questions on that? Any other questions on that? Now, we might say, in connection with your question, by linearizing, are we overestimating or underestimating? Well, notice that, let's look at the following. If I look at the variation in VCA, delta VCA, that's equal to V delta CA plus CA delta V plus delta CA delta V. If I just multiply things out. If I multiply delta C, V times delta CA. So, V plus, so I'm multiplying, actually I should do it differently. Actually, this is correct, but you can think of it as multiplying V plus delta V times CA plus delta C. So you can get VCA, that's the base state, plus V delta CA plus CA delta V plus delta V delta CA. The important thing is, by chopping it off here, this is linear. I only have a delta C, one delta, never two deltas multiplying each other. Here's the quadratic term. By chopping it off, that says I'm underestimating, by chopping it off, I'm leaving something out, and I'm underestimating the nonlinear term. So I'm underestimating what leaves the reactor. I'm underestimating what leaves the reactor. So really more leaves the reactor than I thought. The nonlinear one is more than the linear one in this case. So if more leaves the reactor than I thought, then that says that CA, the true CA, is probably going to be a little lower. So we did this for each of the problems. The true CA, the nonlinear one, is going to be a little lower because by chopping this off, we underestimate. We're taking something and estimating by something that's smaller than that.
But even on that, where it's concave.
Again, I can't.
You ever say before if it's concave, then the linearization will overestimate?
It's the wrong thing that's concave. The input, when the input is concave, But remember, when I was talking about concave or convex, I was talking about one variable that was being estimated, not not CA squared, the square root of CA, the square root of it. So it was easy that way. But here, it's not just one variable, it's two variables. It's the product of VCA. So I don't know what concave means because it's more dimensions. It's not CA squared versus CA. It's VCA versus VMCA. So it would be a three-dimensional plot. It wouldn't be a two-dimensional plot. So that concave convex isn't quite clear exactly how to make that plot. So that's why I needed to do this little analysis of delta VCA. That if you like, think of delta as taking a total derivative. The total derivative. So the total derivative of VCA is the derivative of the first thing times the second, plus the derivative of the second thing times the first, plus another term. Well, here, I would stop here because that's linear. If I'm just taking the derivative, but I'm taking the variation, I also have this term. So we're underestimating. I don't know if that's clear, but that's the idea is that when I have a function, more complicated function, it's not just a two-dimensional plot of your function versus one variable. I have a function versus two variables. So the concave convex argument isn't as straightforward. Yep.
So I get why we're underestimating. I don't get this graph.
Which one?
We are
This?
underestimating this graph.
So
Why is
this one? Because because we're underestimating what leaves. What leaves lowers CA, because it comes in with a negative sign. So more is leaving than I estimated with the linear. So if more is leaving, that says VCA is more negative than I thought. So that means I have a little less CA at the end. I'm glad you asked that, because I really wanted to go through that logic. Other question? Okay, so once we've done that, now what happens if we want to solve the nonlinear problem? Now, it's hard to solve nonlinear problems analytically, so often we do it numerically. And how do we solve, so here you're going to get the 2-minute course in numerical analysis. There's a whole separate course in numerical analysis. There's a whole field of numerical analysis. Just going to give you a little introduction to that. So let's say I have an equation, y dt is f of y and t. And I want to solve that equation, and it's nonlinear, it's complicated. So I want to solve it numerically. So what I might do is I might discretize t, I can make it discrete. And by the way, I want y of t0 to be y0. It's a first order equation, so I need a boundary condition. So I need an initial condition. So I'm going to discretize t into t0, t1, t2. And so now what I would do is, the simplest method is called the Euler method. Euler method says I approximate the y dt by y of ti plus 1 minus y of ti over ti plus 1 minus ti. Delta y over delta t. In which case, I now write, I solve for y of ti plus 1. So if I know, for example, y of 0, I can solve for y of 1. If I know y of 1, I can solve y of t. So I have y of ti plus 1 is equal to y of ti plus f of yt times ti plus 1 minus ti. The only question is, which f do I choose here? The simplest case, so I've got a number of choices. Choice 1 is the explicit choice. With this, I choose f of y at ti. So in the explicit choice, let's start from t0. I know y of t 0. I want to calculate, so I is 0. I want to calculate y of t1. Well, I know y of t0. I know f of y of t0 and t0, because y of t0 is y0, t0 is t0, f is an explicit function, times t1 minus t0. So here, I can solve for y1 in terms of y0, y2 in terms of y1, y3 in terms of y2, etc. This is explicit, called an explicit Euler. The problem with the explicit Euler is often it can be unstable, and it converges very slowly. That is, when you cut delta t in half, the accuracy only goes down by a factor, the error goes down by a factor of 2. What you would kind of like is when you cut the delta t in half, the error should go down by 1/2 to the third or the fourth power. You don't want it to go down just by half, you want it to go down by a 16th. You want it to go down really fast, so that way when you cut delta t a couple of times, you get a very accurate solution. There's also an implicit choice. Implicit says, let this be f of y of t I plus 1. Ti plus 1. Now, so that says, if I know y0, so I want to calculate y1. y1 is y0, t1 minus t0, but now I have f of y1 and t1. Well, I know what t1 is, but I don't know what y of t1 is. Because I've got y of t1 here, and I've got y of t1 here. So the idea is I guess t1 and I iterate. So I guess a value of t1, and then I calculate t1. And then I plug that one back in here, and I calculate a new guess for t1, and often that converges. So that's called implicit, because I have a formula for y of t1 in terms of y of t1. And I have to do iteration to solve it. Is that clear? And that doesn't converge faster, but it's much more stable. Stable means sometimes if you do a little error in the input, you only get a little error in the output. In an unstable system, you do a little error in the input and you get a big error in the output. So you don't want that. So it turns out that the implicit method is much more stable. That in general, implicit methods are much more stable than explicit methods. Now, let's say I want to get a better error. I don't want the error to go down by a half when I cut delta t in half. I want it to go down by a 16th. So I have a third choice here. Notice, if I have, this is t, and let's say here is ti, and here is ti plus 1. And let's say I have y, and then I have f of y of t. So, if I'm looking at this equation, let's say this equation, or this one, now this one, let's do this one. If I want y of t1, in terms of y of t0, plus something times t1 minus t0, do I want the derivative here or the derivative here at the end point? So this would say, if I take this one, the explicit method, I'm assuming that the derivative here is representative of the whole interval. If I take the implicit, I'm assuming the derivative here is representative of the whole interval. Maybe it would be a better idea to try to get the derivative in the middle. Maybe that's more representative of the derivative of the whole interval. And that, if I try to do that, that's called the Runge-Kutta method. And that's a standard way of solving these equations. And there what you do is you take the f of y t, and what you use there is you try to write that as f of y at ti plus ti plus 1 plus ti over t. Ti plus ti plus 1 plus ti over t. I know that's a little fussy, what I mean is the midpoint. You try to get f of y at the midpoint time. Well, how do I get this? The way I get this is the way I did before. I'll just assume that this, y at the midpoint, is y at the left point, plus f of either the left or the right, times the midpoint in time, times ti plus 1 minus ti over 2. So what's the idea here? Instead of choosing f of yt as the left endpoint or the right endpoint, I try to approximate f at the middle. If I try to approximate f at the middle, then I need to know f at the middle is f at y at the middle and the time in the middle. Well, how do I approximate this? I know what this is, because I know the times. Y in the middle, I can go back to the way I did before. Is y at the left endpoint plus some value of f times half this distance. And now you can say, should I choose the left or the right? Well, I can do the same kind of approximation for this f as I did for this f. And if I do that 4 times, that's called a 4th order Runge-Kutta. If I do it 5 times, it's a 5th order Runge-Kutta. And each time you do it, every time you do it, you make the error go down by another factor of a half. So if you do it 4 times, then when you cut the error, the delta t in half, you cut the error in by 1/2 times a half times a half times a half, 16. So typically in most packages, they'll use the 4th or 5th order Runge-Kutta to solve a simple ordinary differential equation. And because they know that the error will go down really fast, either as the 4th power or the 5th power of your delta t. Now, so are there any questions on that? I don't expect you to be experts on Runge-Kutta after this discussion. This is when you're watching a TV show and they have a commercial break and they advertise another TV show. You're not going to be an expert on that other TV show. They advertise that one, so you say, gee, I want to watch that one. So that's what this was. This is the commercial for numerical analysis. A little bit of a flavor of what happens in numerical analysis. Because in numerical analysis, in real life, you want to solve equations that are often too hard to solve analytically. So you need numerical methods for doing that. And a numerical analysis class says, I could probably think of 50 different ways to solve that equation with numbers. How do I know which one has the least error? How do I know which has the most error? So how do I know which one to choose? So in a numerical analysis class, you use simple ideas to develop several methods to solve a particular equation. But the key thing is you learn how to estimate the error of each of those methods so you know which ones to choose. You want to do an integral? There are 50 different ways to do an integral numerically. Which one is the one you should use? And that depends on the error and how hard it is to do. So it often depends on the problem. Any questions? Now, let's note, and I should number the blackboards. When you solve kinetic equations and other equations, often, if you have multiple reactions, as you find in your physical chemistry class or your reaction engineering class, you'll have many rate constants. And sometimes you'll have rate constants with very different orders of magnitude. One of them could be 10 to the 9th per second, the other one could be 10 to the 10 squared per second. Very different orders of magnitude. And when that happens, and you try to integrate your equations numerically with your delta t's, remember, the way you try to get more accurate is you make the points closer together. You make your delta t's smaller and smaller. The problem with that is, in any given computer, you don't have infinite precision. Infinite precision means you would keep an infinite number of digits after the decimal place. You always cut it off. Single precision is 8 digits, double precision is 16 digits. So when you cut it off after 8 or 16 digits, there's round-off error. And the problem is, when you have reactions with multiple reactions with very different rate constants, very different sizes, or other problems where your characteristic numbers differ by orders of magnitude. Those equations are often called stiff. Stiff, like dead, like stiff. And what that means is when you try to get more accurate by chopping delta t in half, eventually you lose more in the round-off error than you do by gaining in the accuracy of the method. The method becomes more accurate, but the round-off error kills you. So you never really converge to the right solution. It's very hard to converge to the right solution with stiff equations. And so there are various ways to handle that. One way of handling it is just to assume that all the fast reactions are at steady state, and then you only integrate the equations for the slow reactions, the pseudo-steady state approximation. But if you don't want to make that, then the idea is you want something that will be accurate and will be stable. And there are implicit methods that are going to be stable. And the one for stiff equations that people use is called Beer's method, which is a fancy version of an implicit method. It's more complicated than this implicit method, but it's an implicit method, and it keeps things stable. I don't want to go into it in any more detail because it's not a course in numerical analysis, but that is an elective course if people want to say they want to take it, it will be offered. I'm sure they also offer one in the math department, but at least the last time I taught it for the math department, and there were engineers and mathematicians. So it's a class that's mathematical, but you all like math, right? Okay, are there any questions on that? Now, this ends chapter 3, which ends the material that's going to be on the first exam. I'm going to give you another homework later today that covers a lot of this linearization business. And I think that the grader said yes. That's what I heard through the grapevine. So hopefully we'll have someone to grade your homeworks. Okay, so the next topic is chapter 4, but let me motivate it. If you remember, when we solved one CSTR with a reaction in it, the algebra wasn't so bad. It was doable. But we also then went to 2 CSTRs in series. And if you remember, the algebra was getting complicated there. And there's a general rule, the more algebra you make, the more likely it is that you do, the more likely it is you can make a mistake. If it's that difficult with 2 CSTRs in series, what if I have 5 CSTRs in series? What's the likelihood that I would get through all the blackboards and not make a mistake? Well, low. So is there another way of doing it? And it turns out the answer is yes. And there's this magical thing called the transform, the Laplace transform. But in general, we're talking about transform methods. But what's the idea of a transform? The transform says, I replace a variable with another variable. And I have to define what that other variable is and how I replace it. But there's something magical. When I take a differential equation in my original variable, it turns into an algebraic equation in the new variable. And I'm much better at solving algebraic equations than differential equations. So I solve it in the new variable, and then I go back to the old variable. Now, it's not obvious that that should work. That's why there's math to prove it works. I'm not going to prove it works, but I'm going to show you how to use it. To prove how it works, you really need a course in complex variables, complex calculus. This is not that course. We're still going to have a fair amount of complex variables to use it, but not to prove that it actually works. So I need to give you some other motivations why we might want to do this. It's very good for solving ordinary differential equations with constant coefficients. It's really good at that. It makes it much easier. it turns out, as we'll see later, that it's going to lead to a method of describing complicated systems in a simple way, in what we call block diagrams. So for example, in this case, we have things that go in and things that come out. Inputs to a problem and outputs to a problem. But I have to draw these complicated pictures. When we write block diagrams, I'll just have a box for each piece of equipment, for the separator, for the reactor, for the heat exchanger, and I'll have arrows going in and arrows going out. And in terms of Laplace transforms, it makes that representation easy and exact. So we'll see later on, block diagrams will be a result. The next thing is, sometimes I would like to know what happens if I have a sinusoidal input coming in, what comes out. And that's very easy to do with Laplace transforms. It's harder to do with ODEs. We can do it with the method of ODEs, it's just harder. It's a lot easier with Laplace transforms. And finally, the notion of stability. If I make a little perturbation from the steady state to the input, does the output go back to steady state, or does it blow up and go to infinity? Remember we said earlier in the semester, if I perturb the steady state in a reactor, does the pressure go back to steady state, or does it go really high and the reactor blows up? I think we want to know that. That's important. So, and that's all easy to do, much easier to do with Laplace transforms than than the usual way. Can you see this blackboard, or do I have to close those screens?
Can you move the one?
Let me close them. How many minutes enough when you can see? That's enough? All right, so for Laplace transforms, I'm going to assume that f of t is 0 for t less than 0. So I'm going to assume that f is 0 for less than 0. And I'm going to define the Laplace transform. So the Laplace transform of f of t, which I'm going to call f tilde of s. So that way there won't be any confusion as to what variable is replacing what variable. When it has a tilde on top, it's the new variable. When it has no tilde on top, it's the old variable. And that's the dependent variable. The independent variable, t, is going to be changed to s. And that's defined as the integral from 0 to infinity of f of t e to the minus st dt. So I have a new variable s. I take f, and I integrate it from 0 to infinity. I multiply by e to the minus st and integrate from 0 to infinity. So now I have something that doesn't depend on t, it only depends on s. And now the question is, when does this make sense? When does it, when does this exist? So, sufficient conditions for f tilde of s to exist. 1, f of t is piecewise continuous. So it's piecewise, it doesn't have to be continuous, it just has to be piecewise continuous. So it can have discontinuities. Doesn't have to be differential. F of t does not grow as fast as e to the st. That is, f of t as t gets big doesn't grow faster than e to the st, so that eventually for high t this dominates and the integrand goes to 0. So the integrand has to go to 0 as t goes to infinity, otherwise the integral won't exist. And of course, the integral has to exist. Has to be less than infinity. And pretty much this is a necessary condition for this. So in all those cases, the integral has to exist. Now, you should also note that, so let's note a couple of things. S may be complex. S can be complex. Does everyone know what a complex number is? So a complex number is the real axis and the imaginary axis. And S could be a value, could be written as vector, where S is equal to S real plus I times S imaginary, where I squared is equal to -1. So this is S real, and this is S imaginary. And you can see that I can also represent this in polar coordinates. I could also write this as some sort of magnitude of S, the length of S, times cosine, well, let me write it up here. S is equal to SR plus ISI is equal to the magnitude of S times cosine theta plus the magnitude of S times the sine of theta times I. Magnitude of S times the cosine gives me SR, magnitude of S times the sine gives me SI. And if I factor out the magnitude of S, then I get cosine theta plus I sine theta. Where, let's note that the magnitude of S is SR squared plus SI squared square root. And theta is the arctangent of SI over SR. So that is the polar coordinate representation. And we call this cosine theta plus I sine theta. We define e to the I theta. Until now, you've only had exponentials where the exponent is real. But in the first day of a class on complex variables, you prove that the only possible definition of an imaginary exponent, e to the I theta, is cosine plus I sine theta. The only possible definition that's consistent with what you know about exponentials, that e to the a times e to the b is e to the a plus b, that e is infinitely differentiable, and that e to the 0 is 1. The only possible definition that satisfies those three properties is this, e to the I theta, and that's something you have to prove. You usually prove that in the first day of complex variables class. Okay, so S can be a complex number. R is real here, but S can be complex. And let's note that this transform, the Laplace transform, is linear. It's linear because it's an integral. So if I had f plus g, I would have f plus g here, and I get the Laplace transform of f plus the Laplace transform of g. So it's linear. And what else can we say? And we'll talk about the inverse as well. The inverse is a bit more complicated, how to go back and forth. Let me note something, that here we take the Laplace transform, and when you do the inverse, there's a complicated formula involving complex variables, which you don't know how to do the integrals in complex variables because you haven't had the course. The way you do it in practice is there are these tables. There's one in your textbook on page 100 with basically two columns, f on one side and f tilde on the other side. And the idea is when you take your equation f of t and you want to Laplace transform it, you look up everything in your equation in the left column and take what and transform it into the right column. And then you do the algebra. You find an answer, you look for the answer in the right column, and you go back to the left column. So maybe you can all bring a copy of the table next time. But what I want to do is I want to prove a few simple things. So, for example, do you have a picture of that backboard so I can erase it? You should get an automatic eraser, like a windshield wiper. Okay, so I claim that the Laplace transform of a constant, is that what I want to do? Let's just see if that's what I want to do. Laplace transform of a constant, yes, is C over S. So let's do the Laplace transform of a constant. That's equal to the integral 0 to infinity c e to the minus st dt. Okay, well, c comes out. E to the minus st dt. And the integral of e to the minus st is e to the minus st over minus s. So that's e to the minus st over minus s from 0 to infinity. Well, at infinity, that's 0. At 0, it's 1. So 0 minus 1 over s is 1 over s. And I lost the c. It's c over s. Is that clear? How about the Laplace transform of theta of t? Where theta of t is the step function that's 0 for t less than 0 and 1 for t greater than 0. And that's called the Heaviside function. One side's heavier than the other. And also because it was postulated by Oliver Heaviside, which is actually true. So this is equal to the integral, well, from 0 to 1, theta of t, e to the minus st dt, 0 to infinity. Well, theta is 1 for t greater than 0, so this is just the integral e to the minus st dt. And that just equals 1 over s. How about one more? Let's look at e to the at and sine omega t. Let's look at the Laplace transform of e to the at, which we're getting close to lunchtime, so that's why I chose an A here, because we're going to at. So that's the integral from 0 to infinity, e to the at, e to the minus st dt. That's the integral from 0 to infinity of e to the minus s minus a t dt. And that's just equal to 1 over e to the minus s minus a t over minus s minus a from 0 to infinity. At infinity, that's 0. At 0, it's 1. So it's 1 over s minus a. If I do the algebra too quickly, just stop me. But I think the algebra is elementary. L of sine of omega t. Well, there are a couple of ways of doing this, but let's do this sort of the straightforward way, even though it's a little longer. So this is the integral from 0 to infinity, sine omega t, e to the minus st. Well, let's integrate this by parts. Let this be u, and this dv. So then du is equal to omega cosine omega t, and v is equal to e to the minus st over minus s. So this is equal to uv sine omega t times e to the minus st over minus s from 0 to infinity, minus the integral v du, minus the integral e to the minus st over minus s times omega cosine omega t. At infinity, the exponential is 0. At 0, the sign is 0. So this doesn't contribute. And now I have a new one that I have to integrate by parts. Let's let this be u, and this dv. So my new u is omega minus omega sine omega t. And my new v, I'm sorry, my du dt. Minus omega sine omega t dt. And v is again e to the minus st over minus s. So this thing is equal to, I've got omega over s times uv. U is cosine omega t, e to the minus st over s, minus 0 to infinity. Minus the integral of dv, minus the integral 0 to infinity. V is e to the minus st over minus s times du. So I've got an omega and another minus sign times sine omega t. So if I haven't made any mistakes, I have this thing, which I'll call A. And here I have A again. So I have the following equation. I have A is equal to omega over s. And at infinity, this is 0, but at 0, this is 1 and this is 1. So I've got a plus 1 over s. And here I have a minus omega over s times a. Minus omega over s times a. So if I haven't made any mistakes, which don't get on it, this is equal to omega over s squared minus omega squared over s squared times a. So that tells me that a is equal to omega over s squared divided by 1 plus omega over s squared is equal to omega over s squared plus omega. And I'm sorry, this is an omega squared. Yeah, 1 plus omega squared. This is omega squared. So I have omega over s squared plus omega squared. Let's see if that's the right answer. Yes, that's the right answer. Miracles do happen. Okay, next. Let's look at theta of t0. What is this? TB plus T0, is that what I'm going to do? Theta of T minus TB. Yeah. Theta of T minus theta of T minus TB over TB. And I'd like to take the Laplace transform of all this. And we'll see why. Let's just see what that function is. That function says, here's t, here's tp. And this goes from 0 to 1 here. And it's divided by tp, so this is 1 over tp. And then I subtract off a 1 beyond here. So it's the block function. It's just a little block. So, well, theta of t, we know, is just 1 over s. And theta of t minus tp, let's see what theta of t minus tp would be. Theta of t minus tp, integral from 0 to infinity, e to the minus st dt. Well, that's the, I can change variables from t to t minus tp. Yeah, so let's change variables from t to t minus tp. So if I change variables to t minus tp, so t minus tp, well, let's just do it here. Integral theta of t minus tp, e to the minus s t minus tp. Well, to get into e to the minus st minus dp, I had to multiply by e to the stp, so I need e to the minus stp here to cancel those. And now when I take dt minus dp, I have to change this from infinity minus dp, which is infinity, and this has to be minus dp. Because t minus dp is minus dp. Okay, so now let's look what we get here. So e to the minus stp. Theta is 0 when t minus dp is less than 0. So even though this starts at minus dp, theta is 0 when t minus dp is less than 0. So from minus dp to 0, this is 0. So this doesn't matter. So this can go back to 0. And then this is just the Laplace transform of theta of something. And the Laplace transform of theta of something is 1 over s. So now I know that this is 1 minus e to the minus st p over tp. One minus e to the minus stp over stp. So this is the Laplace transform of this thing is equal to that. And you'll see why we do that next time. And let's just see where we are. Okay, I'm only one equation away from where I wanted to be, but it looks like we're kind of out of time. So let me just tell you what the next step is, and I won't do it this time. Why did I do this? I did this because I want to take the limit. Notice here I have a box that's of width tp and of height 1 over tp. Next time, the first thing I'm going to do is I'm going to take the limit as tp goes to 0. But what's going to happen? This box is going to get really tall because 1 over tp is going to go to infinity, and it's going to get really skinny because tp is going to 0. But the area of the box is always going to be 1. This is t plus t. And the limit of this thing as tp goes to 0 is what we're going to call the Dirac delta. And you had something reminiscent of this in your homework. There was one problem where they said, imagine instead of a step function, you take a bucket of something and you dump it in. So something happens at t equals 0 and at no other time. And that's what's going on here. The amount in the bucket is the area under the curve. And the amount of time it takes shrinks to 0. And the Dirac delta is a really useful thing. It's not really a function because the integral over a point is non-zero. We'll talk about that next time. Today is Wednesday. When is the holiday? Is Monday a holiday? Is Wednesday a holiday? Okay.